Alright, let's take a look at how to solve a three-phase system. This is the particular problem that we're going to solve here. And before we start parsing through it, let's take a look at our rules that we're going to use for navigating through a three-phase system. So, first, three-phase systems, you can have voltage sources or impedances that are connected in Y or delta. You can use sort of a lumped circuit abstraction to draw a box around the source and around the load. And in between the source and the load, you'll have three lines. And it turns out that you can measure the voltage across a line, or you can measure the current through a line, and that the voltage across two lines or the current through a single line can be created using any combination of Y or delta with the load or the source. And that enables us to simplify some of our problem solving with these kinds of networks. Generally, what we want to do is convert everything into a Y and then solve it. And here's why. If you take a delta network and try and take a look at it, you'll notice that nodal analysis is really complicated. Mesh analysis is also really complicated. But when we look at a Y to Y network, the central node of each Y is connected to the ground, such that the voltage across all of the central nodes in every Y network that's connected in parallel is 0. So what that allows us to do is take a single phase of a Y to Y network and solve it independently of the rest of the elements in the network. And then we can relate that single phase to all of the other phases because all of them will be off by 120 degrees. We have some nomenclature that we use, and that is important to keep in mind, especially when you're parsing through a question and trying to understand what you're being asked. Typically, the source is labeled with lowercase letters at the extremities, and if it's a Y, there'll be an N, a lowercase n, in the center. And the load are uppercase letters. Okay, so you'll know when you're dealing with a Y-connected load if you're given an impedance labeled A to N. And you'll know that you're dealing with a delta load if you're given an impedance with AB, AC, BC, whatever. Okay? Finally, we have these conversions. You'll probably just want to write these down and have them on a little cheat sheet somewhere to refer to until you get accustomed to using them. I won't describe them now. We'll come back and look at them when we need them to solve the problem. So here's the problem, and let's move through it and try and design a circuit that emulates this problem. We have a three-phase balanced delta to delta system that has an ABC sequence. What's that telling us? Delta to delta. Okay, that means we have what we don't want. We have something that looks like this. Okay, it's a really complicated circuit to solve. 4 meshes. It's just a nightmare. We don't want to deal with it. So we're going to convert it into something more simple. Okay? It has an ABC sequence. That's giving us key information about labeling or about assigning the phase angles at the very end of the problem. So we'll come back to the sequencing at the end. Then we're given a line and a load impedance, and those are just for drawing into our circuit. And then we're given a load current. Notice that the load current, well, it's called a load current, which means it's the current across a delta load, but it's also further labeled IAB. Okay? If you go back to the graphic here, we're talking about capital AB. We're talking about a current across a load. So if I were to convert that load into a Y load, do you think that the current is going to be the same? It can't be, right? Because look at this node here. We have 3 branches coming out of the node. When I convert to a Y, I only got 2. Okay, so the current across a delta load is going to change when we convert it. And now we want to know, finally, what are the phase voltages? So when they say phase voltages, they are referring to the voltages of the delta load. Okay, if you have the solution to this problem somewhere on the internet, which I've seen, I don't believe that their answer is correct because they give you a Y phase voltage. We'll cover that when we get to it. So let's notice that the impedance in the line doesn't change, and that goes back to our picture. Just to come back here again, the idea that we can use a lumped matter abstraction on both of these boxes, but the lines don't change. The voltage across the lines is going to be the same no matter whether we convert to Y or delta, and the voltage and the current is going to be the same, and the impedance is going to be the same. Okay, so we do not change the impedance in the line, so we'll just draw it right in. But the load impedance does change, and the load impedance changes by a factor of 1/3. Okay, again, that goes back to our little cheat sheet here, where if we had a delta load, we would have to take 1/3 of it to get an equivalent Y load. Luckily, they've set this problem up so that it's very easy to do that. It's just 3 plus J2. Okay, so we have our IAB, and IAB is not this current, right? Because we just explained why that doesn't work. If we have IAB equal to 15 angle 40, then by our conversion factor, we want to get IA right? Again, let's go back and look at our picture to make some sense of that. What we're going to do is, well, IAN is essentially IAA. So we need to convert this IAB to a current across the lines, across the transmission lines. And we simply do that by using this little snippet right here. Notice that we're going from delta to Y, so everything's backwards. We multiply by the square root of 3, we subtract 30 degrees. Okay, so let's do that. So we multiply by the square root of 3, and we subtract 30 degrees. And we find out that IAA, or IAN, whatever you want to call it, is 26 angle 10 degrees. And that's what this current is. So basically now we're one step away from solving a single phase of our circuit. So we want to know what V is, and this is what? This is VAN, right? Because we're dealing with a Y network. One more time, I'll go back to the picture. Okay, we converted our circuit to this circuit. So we have Y over here, we have Y over here. So when we're looking at this voltage, this is V from A to N. So that's why I say that the solution, if you've seen the solution that's provided, it's not correct, because we want VAB. But first we'll solve for VAN. VAN is simply I times the impedance, so it's 26 angle 10 times the sum of the impedances, which is 3.3 plus J 2.2. And if you plug that into your calculator, you will get 103.1 at an angle of 43.7 degrees. Okay? And if you were to keep it into a Y network, the magnitudes would stay the same from VA to N. Going to VB to N, the phase angle would be 43.7 minus 120, and then for VCN it would be 43.7 plus 120. But we want to convert this back into the delta source, because we want to figure out what those source voltages are for delta, for our delta network. So that's going to be a VAB. Okay, and to calculate VAB, there's a little trick I use if I'm forgetting. Do I divide by the square root of 3, or do I add, multiply by the square root of 3? And it's this. Look, we've got a line. We know the voltage between these lines. And the voltage between those lines is given by either a delta or a Y network. If it was a Y network, there'd be two batteries, parts of two voltage sources across those lines. If it was a delta, there'd be only a single one. So the delta one would have to be larger in order to match the voltages of the two independent sources. That's just sort of my little trick for remembering it. You can also just remember that the line voltage is delta voltage. Okay, so we need to convert this by multiplying it by the square root of 3, and adding 30 to the phase. Okay, so VAB finally equals 178.57 at an angle of 73.7 degrees. VBC equals 178.57 at an angle of minus 46.3, and VCA equals 178.57 at an angle of 193.7. And don't forget that we want to label these V RMS. And those are the phase voltages of a delta network described in this particular problem. Okay? I hope that's helpful. Good luck.